Hi, I'm Chris Brown, and this is lecture 2.17 in axiomatic design and manufacturing processes. So we're going to be talking about toolware and machining and the Taylor equation. So machining economics. Most manufactured goods are no more than 2 steps away from a machine that cuts metal. So the speed at which we can cut metals is a major factor in determining our productivity and therefore our standard of living. But what limits the speed at which we can cut metal? Toolware. So our objectives: understand mechanisms of toolware, show toolware cutting speed relations, and this gets us to the Taylor equation, and introduce optimization of a coupled system. So, cost of cutting tools. So one company here near Worcester makes valves and was spending $1 million a year in cutting tools. But an aircraft manufacturer was spending that much every day in cutting tool inserts, and that was 20 years ago. So the development of cutting tools has attempted to decouple wear and speed. But they are still coupled. Prior to 1900, we're using just hardened steel tools. In about 1900, people figured out how to alloy elements into steels, carbide formers, and these gave steel some hot hardness and better resistance to wear. And so they were called high-speed steel because you could cut faster then. And cutting speeds increased by a factor of 10. Realizing the benefits of this, though, required some adjustments, because if you're cutting 10 times faster, that means you only need 1/10 the number of tools and machinists. By about 1950, ceramic tools had come in, tungsten carbide cobalt composites, which are called commonly carbide tools. And cutting speeds increased by another factor of 10. From the 1970s to the present, we see many kinds of coatings coming in, like titanium nitride, and diamond. And some of these are layered advantageously and in multiple layers. And cutting speeds have been increased in some cases by yet another factor of 10. So note, too, in the context of axiomatic design, that coatings are a kind of decoupling. To decouple the bulk and the surface properties. So you can put on a coating that may not have the fracture strength, for example, the base material, but may have better tribological properties. So here's what the wear looks like on a turning tool. And so this is the rake face where the chip is sliding over. So here is the crater wear, and this is sort of the dominating wear. And so this is the part that gets the hottest and has the highest pressure when the tool is sliding over it. Here's the wear land. So this is rubbing against so it's on the relief or flank face or relief face. And so that's rubbing on the workpiece, and that's wearing there. And we can see some notch wear here and sort of here at the depth of cut position. And so these are where we get special kinds of stresses at the edge of the chip, and so we get special wear conditions going on there. So that's a scanning electron micrograph of a worn tool. So wear mechanisms. Abrasion is present if you get, particularly if you've got abrasive particles in the workpiece for some reason, as you might in a casting. Diffusion. The workpiece or the chip is very hot, and the tool elements can diffuse into the chip. There's chemical reactions as well, and there's chipping and spalling going on, and all of these have thermal components. So temperatures increase with speed in machining. Forces stay about the same as you increase the speed, but the power goes up, of course, with the speed. The forces stay the same. And a lot of this power finds its way into the tool in the form of heat. Numerical simulations can be done to look at the temperature fields during machining, and people have done things like embedded thermocouples or done some clever things to make the tool and the workpiece or the chips thermocouples. And so there's been some work done on looking at the temperature fields, and here we can see this hottest region right in the crater position where we saw the most wear. So there's clearly, wear is clearly thermally activated. We can see some of the temperature field going down into the workpiece. Most of it's going up into the chip. So here are some tool life cutting speed curves. Let me see first. Right, let's take a look at this slide first. So here's what happens. Say if I'm cutting at one speed, a low speed, we start off with some wear here, and this is primary wear where it's going up, and then it's kind of steady state or secondary wear, and then here at the end it accelerates, and at some point we're measuring the wear. It could be the flank wear, for example, but there's some sort of wear on the tool that we're going to measure, and there's some critical point where we say, okay, that's done. That's the life of the tool. Because if we keep going, we're going to break it, or the surface finish is unacceptable or something. So we go, all right, there's the tool life for tool number one, or speed number one. Then we can increase the speed, and we see, oh, it wears out a little bit faster, and a little bit faster, and a little bit faster, as we increase the speed, and the tool life goes down and down. But we get the parts done faster. All right, let's go back and have a look at here. So now if we plot the tool life versus the cutting speed, so we can get a curve here like E, which is annealed and kind of soft. So here's the hardness of the different materials. D is annealed but a little bit harder. And so we can see that the tool life seems to decrease as the hardness of the material increases. Because this is not the entire story. And here we can see relationships with microstructures. So these are different steel kinds of microstructures, spheroidized and pearlite, ferrite, and martensitic, which would be the hardest. And so here's the cutting speed again on the horizontal axis and the tool life on the vertical axis. So what are the problems caused by tool wear? Well, the surface finish gets worse. The machining forces are increased. And that increases deflection, this increases the heat production, and we have more difficulties maintaining tolerances under those conditions. All right, so we've already looked at that. All right, so if we take the typical sort of tool life versus speed equations that are relationships that we've been looking at, it can be fit more or less to a linear sort of thing on a log-log plot. And so then there's a couple of parameters we need to characterize this. So it's linear on a log. So the slope is going to be the exponent. Here's the tool life time. There's the speed. And then there is the constant. So that's the Taylor equation. Now this plot, and therefore C and N both, and those are the two constants we get from the Taylor equation, depend on the machine tool, the workpiece material, the tool geometry, the depth of cut, the width of cut, the coolant. All of those can change those coefficients. So they're quite specific to the setup. So if we solve for T, of course, we can do that. We can have an equation that looks like that. So we know what the tool life is as a function of the speed and the two Taylor coefficients. And so those are derived empirically. Now, so here's a set of Taylor curves. And this is taken from Milt-Shaw's metal cutting principles. And so they're looking at the size of the wear land as a criteria here. And so what we're looking at is some different machining conditions, different feeds, as we see here. So that shows how it changes with the condition. So these wear mechanisms, they're thermally activated. And so this should make us think of the Arrhenius equation. Higher speeds, higher temperatures, So for abrasion, higher temperatures tend to mean softer materials. If it's a chemical reaction, higher temperatures mean faster reaction times, and if there's diffusion going on, faster diffusion rates. So Arrhenius, who thought of this temperature-dependent equation, actually won a Nobel Prize for his work on electrolyte theory of dissociation, so that things go into ions in water. In any event, this equation here shows the thermally activated relationships. So it makes sense, of course, that intuition will tell you that if something gets hotter, the reaction is going to go faster. And this is described by the Arrhenius equation. So at higher temperatures, the probability that two molecules will collide with sufficient energy to make them react goes up. The higher collision rate. There's more kinetic energy and has an effect on the activation energy. Anyway, so it comes down to this sort of equation here, and you can see the variables are explained. All right, so there's an activation energy there. And in any event, thermally activated mechanisms can be used, therefore, for connecting dPs and PVs. So it's good to keep this Taylor equation in mind. I'm sorry, we've seen two equations, the Taylor equation and the Arrhenius. It's good to keep the Arrhenius equation in mind when you're looking at thermally activated systems. So it's this equation is another tool in our toolbox for analyzing manufacturing processes. More specifically, the tool where, which was Taylor's work. So anyway, we've shown that this is coupled with cutting speed and with workpiece material. So there have been advances in tool materials and coatings to reduce this kind of coupling. But optimization is required where coupling cannot be eliminated. So that while we've reduced the coupling, increased tool life with speed, these are still coupled. Thank you for your attention.